Okay, guys, let's get started. The test will be returned on Monday. Key is posted upstairs. Next week's the last week before spring break. You need to get started on your lab report. On Monday, please ask any questions that you have from the instructions about the lab report. Lab report will be due when you come to lab after spring break. The week after spring break, that lab will be the Wittig reaction. So please take a look at that. Wittig, spelled with a W. Okay, handouts going around. There's a white, a yellow. Test 4. Test 4 is largely aldehyde ketone chemistry. We did a very little bit at the end of test 3, aldehyde ketones. We will make derivatives of aldehyde and ketones. There will be a number of derivatives. Acetals, imines. You made an imine in the lab when you reacted your 2-aminofluorine with an aldehyde. Imine is a aldehyde ketone derivative. The Wittig is actually a reaction of an aldehyde or ketone to make an alkene. First thing we can do is look at nomenclature of aldehydes, ketones. That's on the second sheet in the white packet. Everybody have a white and a yellow. White sheets. So the yellow is our outline once we start reaction. Okay, nomenclature of aldehydes and ketones. Of course, aldehydes here. First off, the functional group, the carbonyl H is often abbreviated CHO. Okay? CHO, but that's the functional group. Obviously, the H is not bonded in between the carbon and the oxygen. H doesn't make two bonds. Okay? Ketone, obviously, the groups can be the same or they can be different. That's nothing new. This is just called the carbonyl. Ketones, aldehydes both contain a carbonyl. Amides contain a carbonyl. Esters contain a carbonyl. Carbonyl is not a precise functional group. It's just a component of many functional groups. Specific. The aldehyde group is also known as a 4-mil group. If that was an OH, it would be formic acid. Of course, the CH3 carbonyl is called an acetyl, like acetic acid or acetyl chloride. Acetyl group, 4-mil group. We've learned some of these before. That's benzaldehyde. Acetone we use in the lab. Acetophenone we've learned before. So 2 ketones, common aldehyde. IUPAC nomenclature of aldehydes. Very similar to anything else. Longest continuous chain here would be 1, 2, 3, 4. So we're dealing with butane. We drop the E and add Al. You can call me Al. Is that some? No. Butanal. That's butanal. Not butanol. OL would be what? Alcohol. And you would have to say where the OH is. Here, the one position is the carbonyl. You do not need to say where the carbonyl is. An aldehyde is called a terminal functional group. The functional group is at the end of the chain. What if the carbonyl is at here? Would you call that 2-butanal? No, it would not be an aldehyde if the carbonyl was there. It would be a ketone. You can only have an aldehyde at the end of the chain. It's called a terminal functional group. Butanal, that's it. Name this guy down here, longest continuous chain. The one position by default is the carbonyl, so you might as well start right there with your counting. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Which is longer? 6. So right there is hexanal. What's on the hexanal? At the 2 position, there's an ethyl. 2-ethyl hexanal. Should be pretty straightforward now, just other nomenclature. Ketones. Longest continuous chain, 1, 2, 3, 4, 5. It's a pentane. But this is a ketone, so we replace the E with -one, and it becomes pentanone. So that's pentanone. Well, if that's pentanone, what is this? It's also a pentanone. See, with ketones, the oxygen could be here or here. It's still ketone, and this would be a structural isomer or a constitutional isomer. With ketones, you have to say where the oxygen is or where the ketone is. Here, the end is not at the carbonyl because that's not the end of the chain. It's at the end closest to the carbonyl. So that would be 1 here, and that's 2. Carbonyl's at the 2, and so this is 2-pentanone, with the 2 denoting where the carbonyl is. So if that's 2-pentanone, what is this? Either way you go, it's 3. So this is 3-pentanone. Constitutional isomers. They have different names. Okay, terminal functional group that's mentioned there. There's one name down here. Longest continuous chain. 1, 2, 3, obviously not. 1, 2, 3, 4, 5, 6, 7. That would be a heptanone because it is a ketone. Where's the carbonyl? 3 positions, so that right there is 3-heptanone. What's on the 3-heptanone? A methyl is at the 2 position. 1, 2. Or you can say 1, 2. Either way you go, that's the 2 position. If you come through here, that's the methyl. If you come through here, that's the methyl. 2-methyl, 3-heptanone. With ketones, you can have a ring with the carbonyl in the ring. You cannot have an aldehyde in the ring. That has to be an H, and it couldn't be a ring. These are quite common. If there was no carbonyl there, what would that be called? Cyclopentane. So it's just like above, you replace the E with -one, and it becomes cyclopentanone. Let's replace the E with cyclopentane. We just replace that E with -one. Cyclopentanone. The one position by default is the carbonyl, so you really don't have to say 1-cyclopentanone by default. Okay? Carbonyl is the 1. So if we had a chlorine here and a methyl there, what would that be? It's either a 3,4 or a 3,4. I'd put it in alphabetical order. I would say 3-chloro, 4-methyl, cyclopentanone. The ketone is by default at the 1 position. That look right? So sort of like when we named aromatics, and the substituent was at the one position. Like benzoic acid. That carbon that had the acid was at the one position. Any questions about nomenclature? Should be pretty straightforward. There should be some in the book to work. Aldehydes, ketones. We will go back to comprehensive spec problem for test 4. There's a review of aldehyde ketone NMR on the next page, and a review of mass spec of aldehydes ketones. All that's a review though. I just include it because I'm a nice guy. You understand? All right. There's a number of applications in this here package. Pretty much the rest of it is sort of just miscellaneous applications. Aldehyde ketone chemistry is very diverse. Also very important, especially when you get to biochemistry. A lot of biochemical transformations involve aldehyde ketone chemistry. There's a handout in here that talks about vision and how retinal, which comes from vitamin A, retinal ends with an AL. What does the ending of AL tell you? It contains an aldehyde. Vitamin A contains an OH. It gets oxidized to the aldehyde, retinal. Retinal reacts with opsin, make an imine, and that molecule sort of mediates the collection of light in the eye. There's a handout about this. There's a warm-up here, some drug applications. Basically, there's a number of applications. Let's look at the chemistry. Two main areas of chemistry we'll be doing for test 4. The yellow here is one, just the first half. Which need part? Yellow. Then there'll be one other outline. This one focuses on the carbonyl. So we carbonyl here, chemistry here. The second half of this material will focus not on the carbonyl, but next door. Because these H's over here have some acidity, we can make an anion over here that's resonance stabilized, and so we can do chemistry next door. So that'll be later in a couple of weeks. For now, we're doing chemistry at the carbonyl. Okay, two types of reactions. Roman numeral 1 and Roman numeral 2. Non-reversible. Now the reaction is we're going to add a nucleophile to carbonyl. We've been doing that for 3 weeks at least. But the nucleophile can add, typically nucleophile has a lone pair. We can do a nucleophilic addition, and that would give this here, tetrahedral intermediate, nucleophile added, electrons up. Non-reversible means that once the nucleophile adds, it ain't coming off. That is, this is not going to come back down and kick it back off and go back here and expel the nucleophile. Not reversible. At this point, the only thing you can do is just work it up, supply a proton by acid or water, put the proton on, and there you go. That's your end product. And we did a couple of these at the very end, like adding a hydride. We're adding a Grignard. This is basically methyl anion, right? This adds electrons up. You get such an intermediate methyl with an O minus. You add in water, the O minus picks up an H. Okay, everybody see the new H, that H there? It's amazing, but at the end of Organic 2, I still have questions in the past. What happened to the H? Okay? There's an H there, right? Very simple idea, but over the years I still see. Please make sure you recognize simple things. Those are non-reversible. That's it. What type of reagents do this? Hydride, LAH, alkyl and real alkynyl. Basically, can the nucleophile turn around and be a leaving group? We know a methyl's not going to leave. We know what H isn't going to leave. A plain carbon's not going to leave. The next type of reactions will be reversible. These will be ones where the nucleophile can add, but then this could reverse. This could come back down, the nucleophile could get kicked off, and we can go backwards. That means it's reversible. That doesn't mean we can't continue on like up above, put the proton on, get this. And we may even continue on further. The nucleophile may somehow move in and kick the OH off and make a double bond. Because at this point, the nucleophile could leave, and you could go backwards, but that could also leave. Typically, this happens when the nucleophile has a lone pair, and it can move in and kick that off and make that pi bond. So very generic at this point. The main thing is, we're already under Roman numeral 2. And we will be under Roman numeral 2 for a couple of weeks. All the reactions we're doing are going to be reversible. That is, anything we have made, we can go back to the aldehyde or ketone. Okay? In the end, I would hope that you don't just read this for a millisecond and gloss over and continue on. What is the meaning in here in this introduction? This is the foundation. Okay, let's do some examples. Roman numeral 2a. Eventually we'll be on 2g. But we're always going to be under reversible. Okay, enough of that. The first is going to be simple additions. The next ones will be not so simple. Okay, simple addition. The first thing we can do is react with water. Now, my example here is a ketone. It could be an aldehyde. We're doing aldehyde ketone chemistry. Everything we do applies to both. My example may be one or the other. This happens to be a ketone. Okay, we can add water. If you add water to a ketone, we can get a product that looks like this. It's called a hydrate. Why is it called a hydrate? Because we added water. It's also known as a gem-diol because it's got two OHs on the same carbon. Gem meaning twins. It's like there's twins on that same carbon there. Okay? Now, this is a functional group. We need to know these functional groups that we introduce. Most of them I put in bold throughout. So diol. This is reversible. Of course it is. We're under Roman numeral 2. If you have a diol, what can it reverse back to? Ketone aldehyde. Plus what? Make this plus what? Water. It gives off water. Okay? Now how can this happen? Mechanism. First off, it can be catalyzed by acid or base. You can actually do it without a catalyst. Let's do it without a catalyst. What do you want to do first? Somebody said something? We're doing it without a catalyst. No acid. Water is not a strong acid. We can't protonate unless we have a strong acid. What do you want to do first? Nucleophile adding carbonyl. Yeah, that's what I did up there. Nucleophile adding carbonyl, just like that. When that happens, what do we get? O minus. Methyl. What's here? Water added, so we have it's a plus charge. That's just where water did a nucleophilic addition to a carbonyl. That's a simple addition. Simple nucleophilic addition. What do you want to do next to get final product? H plus transfer. You see it? What do we need to do to get final product? This H plus needs to come off with that oxygen and needs to go on that one. We've been doing proton transfers for a month now. That's it. Water adds proton transfer. There's your diol, your gem diol, your hydrate. Where have we seen hydrates before? Oxidation. Remember when we oxidized an aldehyde to the carboxylic acid? We didn't just remove H's, we actually added oxygen. And I told you that it first makes the hydrate. This reacts with water, makes the hydrate. Then we lose two H's and make double bond. When you make double bond, then what do you have? I need to pull out that handout. It's at the bottom of the box. Oxidation of, go back to your oxidation handout, week 2. Hydrate was listed, and I said we'll see hydrates later in the course. Well, later always comes, if you're lucky. And later is now. There's your hydrate. It's a simple addition of water with a proton transfer. Now, a couple of things. This is actually an equilibrium, okay? And most of these are not stable. And the equilibrium highly favors the carbonyl. If you put acetone in water, you get a little bit of hydrate form. But the majority of it stays as the ketone form. It's almost impossible to isolate a hydrate. That doesn't mean it can't be an intermediate in a mechanism, because down here, if this is in the presence of water, this equilibrium sets up, and maybe it's 1,000,000 to 1. That is, only 1 of 1,000,000 exists as a hydrate form. But that 1 gets oxidized to this, and so when this is removed, what happens to this equilibrium? It adjusts in 1 more forms. And when that gets removed, what happens? It adjusts in 1 more forms. And before you know it, all that has adjusted and moved on, even though that equilibrium is not favorable. So a non-favored species can be an intermediate in a mechanism. It's just pulled on by Le Chatelet. So you pretty much can't isolate these, but they're important to know about in mechanisms. You may see them in biochemistry. Some you can isolate. For example, this is called chloralhydrate. That exists in this structure. Question. What does this convert to if it's, I might as well tell you, clarify, if it loses water? What does it go to if it loses water? Right here. I mean, what if that loses water? What does it go back to? The carbonyl. You got to realize and be able to go backwards. What type of derivative is this? Is this an acid derivative? Or an aldehyde ketone derivative? And an acid derivative, such as an ester, that's an acid derivative. How many bonds to an electronegative atom does the carbon have? 3. All acid derivatives have 3 bonds to a more electronegative atom. How many bonds to a more electronegative atom does this have? 2. How many does that have? 2. You see, this is at the same oxidation state. This is an aldehyde ketone derivative. The only way for it to become a carboxylic acid is to be oxidized, and I don't see an oxidant anywhere on the board, which is usually going to be like a heavy metal, chromium or something. There's no way to go from this to an ester without oxidation. This is an acid derivative. It's an aldehyde ketone derivative. Guess what? Everything we're going to be making for the next 2 or 3 weeks are going to be aldehyde ketone derivatives. The carbon will have how many bonds to a molecular negative atom? 2. Not 3. We're doing aldehyde ketone. Okay? Let's just go back to if it loses water. Well, what is this? This is a hydrate. You've got to recognize what a hydrate is. If a hydrate loses water, what do you get? You get aldehyde or ketone. But which one would you get? There's an H here. If it loses water, what do you get? You get the aldehyde, right? I mean, it's just going backwards here. Now, how can we go backwards? Well, just look at it. Anytime you make a pi bond kick off a leaving group, that's easy to do. What does that give? See, that H is there. You don't have to draw it in. I just draw it in with aldehydes. Plus what? Hydroxide? What do you want to do now to get a neutral product? This takes the H. What do you get? You get that plus what? Water. Plus water. That's the water we said we were going to lose and liberate. Okay? Reverse. All these reactions are reversible. Why? Because the nucleophile can also be a leaving group. That's what we said here. Nucleophile can be a leaving group. So you need to be able to realize to go backwards. All acid derivatives can be converted back to carboxylic acids. All aldehyde ketone derivatives can go back to aldehyde ketones. It's going to be an aldehyde because there's an H on the carbon. Questions? So why is most hydrates are not stable at equilibrium? Why is chloral hydrate stable? Chloral hydrate is also, anybody who watched gangster movies from back in the 30s and 40s, they slipped him a Mickey. They were slipping him some chloral hydrate. It's a sedative, quick sedative. Knock somebody out. I mean, that's basically acid aldehyde. I mean, if that's a CH3, that's acid aldehyde. If you drink ethanol, I don't know why you want to do that, but if you drink ethanol, your body oxidizes it to the aldehyde, and it's actually the aldehyde that has the sedative properties of ethanol. Well, it's very similar, but it's even more potent when the chlorine's there. Why is it more potent? Okay, well that's a pharmacology question to get to, all based on structure. Why is this hydrate stable? I'm not going to talk about it right now. I want someone to tell me why that hydrate is stable, where if it was just a CH3, it would not be. Something to do with the chlorines, obviously. Somebody tell me next time why that hydrate is stable. Okay? Okay, so most hydrates are not stable. They're important to know about. Next reaction, simple additions. Instead of water, we can add HCN. If you add HCN to an aldehyde or ketone, you get a cyanohydrin. Let's first do this. Now, the carbon doesn't really have a lone pair here. The carbon adds, not the nitrogen. So I'm going to have to somehow get a nucleophile. Before I added water and had a lone pair. But this is an acid. It's not a strong acid, but I'm going to call it H plus CN minus. Okay? So So I'm going to say it's acidic enough to be ionized enough to have cyanide. Well, now in the cyanide form, I can have a nucleophile, and these electrons can do a simple addition, and we can get Cn, and this becomes O minus. How do we want to get final product? This just needs to pick up an H plus. Where do you want to get that from? The other component right there, if we call that ionized, these electrons here, and boom, there's your cyanohydrin. Nucleophile added, electrons up, and the oxygen picked up an H. So what did we add? We added Cn and H. We added HCN. Okay? Aldehydes and ketones will react with HCN to give cyanohydrins. This name is similar to, you remember these from organic 1? If that was a chlorine and that was an OH, it would be a halohydrin. Now in organic 1, you made, this is a geminal halohydrin. Organic 1, if you react this with chlorine and water, what'd you get? Something like chlorine and OH, something like that. It was a halohydrin, but it was vicinal. The one I showed is geminal. Halohydrin, this is a cyanohydrin. Kind of analogous. Cyanohydrins typically, the most common are your geminal, where they're both on the same carbon, because they come from aldehyde ketones. Now, cyanohydrins can be made and isolated, in contrast to hydrates. These are stable, can be isolated. It's just a simple addition and pick up a proton. Now, of course, what's the reverse? Take a cyanohydrin, what can you reverse it to? Now, this may actually not look like, how many bonds to a more electronegative atom here? Looks like it's only one, so it looks like, hey, is that an aldehyde ketone derivative? So that's not strictly a more electronegative atom, but because of the dipole here, and because it's a nucleophile, it is an aldehyde ketone derivative. Okay? This can reverse, because anytime you can make a pi bond, kick off a leaving group, that's easy to do. Matt?
Is the fact that the carbon is sp have anything to do with it too?
That helps. That helps it be a leaving group because it helps stabilize the Cn minus. So if you do this, what do you get? You get that plus your leaving group. I mean, anything can leave. If you've ever seen it minus, it can leave here. Make pi bond, kick off leaving group. Have you ever seen Cn be minus? Sure. Sodium cyanide, all the time, you see it. The only thing that cannot leave here is like a plain H or a plain carbon. And then what do you do here to get neutral? This takes the H, go here, what do you get? You get your carbonyl plus HCN, so you go backwards. But this can be isolated. To go backwards, you have to kind of heat it, or give it some time, or maybe a biological enzyme can make it go backwards. Two things. If it goes backwards, what do you get? Aldehyde or ketone, depending on what was on this carbon when you reform carbonyl. What else do you get? It's in the box. HCN. What do you know about HCN? It's a gas. It's also deadly toxic. Okay? So, what do you think about the toxicity of these? They potentially reverse if they get in your body. If it reverses, what's it going to liberate? it will liberate HCN. Okay? Cyanohydrins themselves can be toxic because they liberate HCN. Cyanohydrins, where are they found in nature? You ever heard of, they're in the pit of stone fruits, peaches. You ever heard of a pit of a peach contains cyanohydrin, cyanide? It contains a cyanohydrin. But you get these in your body, heat, biological enzyme, it reverses, liberates this, and you're toxic gas. About 10 years ago over in Africa, some country, all the cows were dropping dead. After some research, they figured out what was happening. The hay that they were being fed had been infested with some type of organism that produced a cyanohydrin. The organisms produce molecules. We saw that seminar the other week, last week. And so the hay became, a lot of this was in the hay from the microorganism making it. The cows were eating it, and what happened to the molecule when it got in the body? Somehow it reversed, started liberating HCN, cows were dropping dead. They figured out what it was. One of the handouts talks about this, or some application. The bottom of this page over here. The cyanohydrin that's found in nature a lot, especially the pit of like peaches. Most people don't eat the pit of a peach. Looks something like this. But right here, what functional group is that? Now, it's not precisely an OH, so it's not precisely a cyanohydrin. We've got to get to them. It's actually two functional groups. In a little bit, we'll see an acetal. That's a carbon with two oxygens. This is a carbohydrate, very common in nature. Kind of a sugar moiety carbohydrate that is linked here. This can reverse to liberate this. Liberates that first, but now what is this? Cyanohydrin. This can now lose HCN and reverse to the carbonyl. So you can read about that if you're interested in the cyanohydrin in nature type stuff. We'll see acetals in probably by Monday. So it's actually two conversions to get to HCN. Take a look at that. So, how do you make cyanohydrins? React aldehyde and ketone with what? Toxic gas. Okay. If we wanted to make one in lab, what would you think about pulling out the toxic HCN gas?
I would opt out.
Now, if something happens to the valve and it starts spraying out HCN gas, it'll chase you around the room with the gas. Not the most convenient thing to work with. Can we do this reaction another way? Yes. Instead of using HCN, we can use other reagents. What do we need to do that reaction? We need a cyanide source, and we need an H+ source. Those could come from something other than HCN. Cyanide could come from KCN. And that's cyanide and K+. There's your cyanide. And the H+ could come from sulfuric acid, or maybe this. We've never used this salt. Both of these are solids. Much more convenient to weigh out solids. If you spill them, you can just sweep them up. They're not going to chase you around the room and go into your lungs. Much more convenient. So this is your cyanide source. Cyanide adds. Okay. Then up there we need to pick up a proton. This is your H+ source. Now this is unique. We haven't used that before. That's the monosodium salt of sulfuric acid. Why use that? Why not just use H2SO4? H2SO4 is a liquid. If you ever use it a lot, it's always getting on you. It gets on the cap. It rolls down the bottle. Okay, it's very corrosive. This is a solid. It's a solid H plus source. Weigh it out on the balance. Okay? But it still has one acidic proton left. Okay? Sulfuric acid is diprotic. Well, this still has one proton left. That one proton is still acidic enough to be an H plus source. Okay? So it's just a practical thing. It's just a solid H plus source. Two solids versus a gas. Which would you rather use? Solids. Same mechanism above. Just okay. Chemistry. What if you took the cyanohydrin and heated it with aqueous acid? What might you get? Final exam is what, about a month? What can happen to that molecule with aqueous acid? Protonate the alcohol and and then do what? Leave, make carbocation. What would attack carbocation? Water, and reform this. You're not going to get anything new. There's no nucleophile here. Unless you used HBr. But this would typically imply sulfuric, something with no nucleophile. You're not going to get anything there unless you have a nucleophile. So what? Water. Water and acid, that's hydrolysis conditions. What are you going to get? Can you hydrolyze anything? How about that? Nitrile hydrolyzed for the carboxylic acid? Did we just do that a week ago?
No.
You see, you can't forget your old chemistry. Especially when the final exam is comprehensive over organic 2 and 1. I mean, the nitrile you can do chemistry with. You can do chemistry with the OH, it's just, under these conditions, I don't see what you can do with it. There's no nucleophile. Okay? Those are two examples of what I call simple additions. Just nucleophile adding, and then you pick up a proton to make an OH. But the difference is the nucleophiles that added can be a leaving group, and so you can reverse. That's why we're in the Roman numeral 2. A were simple additions. B, I could have said not simple. It's not that they're difficult. It's just we're going to do a little bit more. Here we're going to do additions with loss of water. Importantly, the carbonyl oxygen is going to eventually be lost as water. It's like that oxygen will eventually be lost as water, and we're going to get something else. So we're going to add a step into the mechanism, and instead of being just simple, it's going to be simple with another step. Call it what you want ever. For example, if you take an aldehyde ketone, reacted with an alcohol, such as ethanol, you do need two equivalents. H plus catalyst, your choice. You can get this with a carbon with two oxygens. Call it acetal. Now the oxygens have R groups. If that was OH-OH, what would that be? That'd be a hydrate. So it's analogous to a hydrate, but each O has R groups on it. And this comes not from water, but from an alcohol. But you actually need two alcohols. And if we star this oxygen, which oxygen is it now? Carbonyl oxygen is eventually lost as water. Where's the star now? This oxygen is going to be lost in water. Okay? Now, you guys should be able to do this mechanism. At this point in your organic chemistry studies, there ain't a lot of mechanisms that are going to be new. That is steps. It's just how do we work towards getting that? Okay? What do you want to do first? I told you, when we're under acidic conditions doing carbonyl chemistry, the first thing you want to do is protonate. Protonate carbonyl. Okay? This can be sulfuric, it can be HCl, it can be sodium bisulfate, dry acid. It can be tosyl acid. Your choice of a strong acid. What do you want to do next? Nucleophile add. What's your nucleophile? Ethanol. Ethanol add. Can I just call this portion R so we can shorten it a little bit? Oxygen added, we have an H and an ethyl and a lone pair. That happens to be a plus charge. This is now what? OH. And what else is there? A methyl? So there you go. That's just a simple nucleophilic addition to a protonated carbonyl. What do you want to do next? Proton transfer from this oxygen to... Okay. Now why would you want to do that? Right. If we must draw it on the other side, I'll draw it on the other side. Proton transfer. I mean, why should the proton get to sit on that oxygen? Why come it can't sit on that one? They're equally as basic. Now what you want to do? Anytime you make a pipeline kick off leaving group, it's easy to do. So there's the loss of water. Now, if this had made pi bonding kicked off leaving group, we would have come backwards. And it certainly could, because that's reversible. We're under Roman numeral 2, which means everything's reversible. But if the proton gets transferred and then this guy kicks that one off, we get to this point. Now, that is not a neutral molecule. How can we go neutral? A lot of times we go neutral by losing the proton. There's no proton here to lose to go neutral. I mean, we could have lost that proton or this one and go neutral, but how do we get neutral here? And how do we get the final product? And why do we need two equivalents? At this point, the only way for this to become neutral is to give it some electrons from the pi bond. If this comes in and these move here, what does that give? See, that gets this lone pair back. That becomes neutral. What added here? Oxygen with ethyl and H. And that is plus. How do we get final product? Something takes the H. There's got to be a minus here. What acid did we use? I didn't hear you. Let's say, okay, we use sulfuric acid, so there's a minus there. This minus can take the H. These thing behind, we get that plus the sulfuric acid reform. This reacts with two equivalents of ethanol to give acetal plus water. This is a true equilibrium reaction. How would you drive this reaction to the right? You can remove water as it's formed. The problem though, we mentioned this problem before. The boiling point of ethanol is 78 degrees. The boiling point of water is 100 degrees. If you try to boil the water out, your ethanol will boil out first. So you can't boil it out. How do you want to remove the water?
Drying.
Maybe a drying agent, molecular sieves. Sodium sulfate might help dry it up. Can we add extra over here? What do you want to add extra over here to push it that way? It says 2 equivalents, but usually when you do this, you just use a huge amount. 2 equivalents is the minimum. Okay? You actually want to use a large amount of ethanol, and that will push it to the right. Let me finish up here. Every step is reversible. The acetal can be converted back to what? The carbon has 2 bonds to a more electronegative atom. That's aldehyde ketone derivative. They all go back to what? Go back here. If we go back, what do we react it with? Water and what? Catalyst, which is what? Water and acid, which is H3O+. You need to look at the reverse of this. We'll finish this up. And look at every step here is reversible. Okay? Every step is reversible. If we have an acetal, could we protonate one of the oxygens? Yes. Then could this kick that off? Yes. Every step is reversible. We're out of time. Please do the reverse reaction. Okay guys, there isn't one seminar today. If you need a makeup, Science Hall, pretty sure it's in the regular room. I didn't check though.
No, because your cabinet.
Oh, yeah, true.
Yeah.
Saying it wouldn't cool it when you keep on cool?
And then you can more stress on that carbon.
It's got 2 options here. It's got 3/4 here. Keep thinking something a little bit more deeper, more clear explanation. This one. Are you listening?